Great, so this is the last chunk of video for this session today. There are more complex models than JC69. Of course, JC69 is the simplest model for nucleotide data. And we have here a list of models with increasing complexity. K2P for Kimura model with 2 parameters. Has equal equilibrium frequencies for the 4 nucleotides, but 2 exchangeabilities. There is 1 exchangeability for transitions and 1 for transversions. So the exchangeability for transitions is higher, and the exchangeability for transversions, because transversions are less common than transitions. So we have 2 parameters, alpha and beta, instead of 1 parameter, alpha. F81 stands for Felsenstein. Joe Felsenstein is one of the big names in phylogeny, and he developed this model in 1981. This model F81 has 4 parameters. There is this time 1 single exchangeability rate, but 4 different equilibrium frequencies. Okay, A, C, G, and T. Now I say 4 parameters. I say 4 parameters to mean 4 free parameters, because you know that the sum of pi A, pi C, pi G, and pi T is equal to 1. So instead, there are in fact in these there is only 3. There are only 3 free parameters. Okay, so when we say free parameters, it's the number of parameters minus the number of constraints linking these parameters between them. Okay, so here we have 3 free parameters for the equilibrium frequencies plus 1 exchangeability rate, so it's 4 free parameters. F84, HKY, HKY for the name of 3 Japanese researchers, Hasegawa, Kishino, and Y for Yamamura, or something like this. 5 parameters, so different equilibrium frequencies and 2 exchangeabilities. So it adds 1 parameter compared to F81, and GTR stands for General Time Reversible. That's the most complex time reversible model on nucleotides, and it has 9 parameters. So beware, using the most complex model on small data sets is not always the best strategy, because the more parameters you use, the more data you need to train or to estimate these parameters. Okay, and if you have too small data set, you are doing what is called overfitting. It means that you're learning parameters that are too tightly coupled to the training data that you're using, and these parameters are not usable for any other purpose than just the alignment you're having as a training data, and also it because of this overfitting, it has some bias in the estimation of divergence times. So these all these models on nucleotide data, those I presented in the previous slides as well as others, are here recapped in this graph. The image credit goes to Professor Guy Perrier from the LBB in Lyons in France. Here you see each box corresponds to 1 model of evolution on nucleotides, and you have the name of the model and also the canonical name of the parameters that are mentioned in the box. The y-axis is the number of free parameters, starting with 1 and up to 9. So the simplest model is at the bottom, the most complex model is at the top. And you have dependencies here because arrows denote that the end of the arrow as a model is just a simplification of the model at the origin of the arrow. For instance, if you want to move from the Chimera 2 parameter model to Jukes and Cantor, you just have to add this additional constraint. If alpha is equal to beta, you get your JC model with one parameter alpha. Remember that these are two exchangeabilities. There is one exchangeability for transitions and one other for transversions. Sorry. If you equal these two, then you have just one free parameter. Okay, so F81, for instance, it has 4 free parameters. The equilibrium frequency of G is not mentioned because it's 1 minus the sum of these 3 equilibrium frequencies. But if here you set pi A is equal to pi T is equal to pi C is equal to pi G is equal to 1/4, then you get to your JC model, okay, with this additional constraint. So you have here a hierarchy of models, and the most complex model is here, okay. As we go up into this tree, the names of these parameters no longer are standard. Like these are exchangeabilities between nucleotides, but I can't tell you to which pair of nucleotides correspond each of them. Okay, it's just for reference that I provide you with this network of models, just so that you can see many of these models have been designed over the time, and most often now, when you have a significantly large data set, you would use the GTR model, general time reversible. The drawback is that all computations are slightly more expensive with the GTR model than with the JC model. So the process of phylogenetic inference is slightly longer if you use GTR than if you use JC. So for amino acid, how is it that my window is not properly fitting the screen? Sorry, yeah. For amino acid data, you also have models. I'm not going to present each of them here. These models are based on a matrix of instantaneous mutation rates or substitution rates that are matrices of 20 rows by 20 columns, because the alphabet of amino acid is composed of 20 characters. And these matrices of amino acid substitution rates have been developed empirically by studying a large amount of aligned protein data and seeing how often do you have an observed difference, an observed substitution between this amino acid and that amino acid, and more or less by analyzing how frequent are some substitutions compared to others, we have designed these models for amino acid substitutions. For instance, you may know that amino acids I, L, and V, isoleucine, leucine, and valine, are very similar to each other. So of course they will have higher exchangeabilities than other pairs of amino acids. So JTT 1992 first matrix built from a large number of pairwise alignments, Jones, Taylor, and Thornton. You have WAG, later on Whelan and Goldman, also from analyzing large number of line sequences, and LG, Lay and Gasquel 2008. The last general purpose protein alignment, protein evolution model, sorry. So it's been increasingly large data sets that have been analyzed in order to evaluate these matrices of instantaneous substitution rates. And you have some specific non-general purpose matrices, like MTREV is for mitochondrial protein data only. So that's it for this second day of the molecular evolution and phylogenetics module. I hope you enjoyed it, and see you soon.